Well, C is a parameter which is constant for this same combination of, say, workpiece material and also cutting tool. As long as cutting tool doesn't change, as long as workpiece material doesn't change, the value of the C also remains the same. And it has got a very important interpretation as well, that is C is representing the cutting speed, giving us a tool life of 1 minute. Let's take a look at the previous equation here again. Okay, in this equation, if the value of tool life, which is T, is equal to 1, then it doesn't matter what the value of the exponent is, because it always gives us a value of 1 for what is in here. And then this practically eliminates this bit of the equation, leaving us with only V that is equal to C. Cutting speed, giving us a tool life of 1 minute, is equal to C. So that's the other interpretation of this value. Okay, moving on. Now let's get started with the first problem of this tutorial session. And in this first problem, we have got a situation where tool life tests on a lathe in a turning machine have resulted in the following data: a cutting speed of this much, a cutting speed of 112, this is considered as V1, is 112 minutes. And this results in a tool life of this much. So this is T1. At the cutting speed of 82 meters per minute, this is V2 now. The tool life was 53. So when we reduced, say, sorry, it should be T. When we reduce cutting speed, then we increased the tool life from what it was to T2. So this is T2. Okay, determine the parameters N and C in the tool life equation. So this is the tool life equation which I have written down here, the only equation we have got for this session on the equation sheet for this session. If we are provided with two different values of V and two different values of T, then we need to compute the values of N, which is the tool life exponent, and also C, which is the constant value. And in part, it is asking us, based on the values of N and C that are to be computed in part A, we've got to see what is the likely tool material used in this operation. And in part C, we've got to use the equation and compute the tool life corresponding to a cutting speed of 90 meters per minute. And in part D, we've got to compute the cutting speed that corresponds to a tool life of 10. Now let's get started with part A. On the basis of the information given, we have got two values of T and also two values of C. And then we need to compute the values of N and C that are unknown. Well, what comes to your mind? How do we do this problem? We are given with two different scenarios, V1 giving T1, V2 giving T2. Then we have got this single equation, Taylor's equation, and we've got to work out the values of N and C. How do we do this problem? Well, we make use of the problem and substitute the values of V and T in the equation for two different scenarios. Okay, that's how it is. We write the equation, Taylor equation for, say, first scenario. We've got the value of V, which is equal to 112, and the value of T, which is equal to 5.5. N and C are known at this stage. Second scenario. V is 82, T is 53. N and C are known as well. However, we know that the value of C doesn't change as long as the cutting tool doesn't change and the workpiece material doesn't change. So these two C values are the same. What do we do now? Of course, we can equate these two equations with one another. If we equate equation 1 and equation 2, then we end up in a single equation with only one unknown parameter. So we don't need to make use of C anymore. If we equate what is left, then we have one equation and a single unknown parameter in it. So it makes it possible for us to compute the value of n, which is the exponent, unknown value exponent, which is still there. And in order to make that happen, we've got to make use of the logarithm, natural logarithm. We can take the natural logarithm from both sides, making it possible for us to compute the value of n. So we do it this way. Okay, we equate the two equations up here and simplify the equation up to this point, and then take the natural logarithm from both sides. Taking the natural logarithm from both sides results in this, and then it will be easy for us to compute the numerical value of the natural logarithm of both sides, and also eventually compute the value of n. So we can compute the value of n. Because the values of t and v in two different scenarios are given, it is possible for us to compute the value of n. Well, don't forget that you need to take the natural logarithm from both sides, because n, the unknown value, is in their power. So we've got to take the natural logarithm in order to make it possible to compute the value of n. Okay, now we have computed the value of n. If the value of n is at hand, again, we make use of the equation up here, substitute the values of one of the two scenarios given. V1, T1, n is now computed. You can easily compute C. Or you can make use of the values of V2, T2. The value of n is the same, and again, you can compute the value of C. To be on the safe side, do it in both ways, and you should get the same value for C. Then it proves that the solution is correct. So we do the computation of this first scenario. We get the value of C, which is this much, and then we also check it by doing the computation of C again, by making use of the information given for the second scenario. And it gives us again the same value of C, meaning that the computation is correct. We still are achieving the same value of C, which is the constant value, as long as cutting tool material and tool material do not change. Okay, any questions on this? Well, we are done with the computation of what is requested in part A. Now we've got to move on to the second part, which is part B. In the second part, which is part B, we are asked to, in part B, we are asked to compute the tool material, to find what is the tool material on the basis of the computed values of n and c. We have the values of n and c at hand. Now, how do we determine the tool material? We've got to take a look at the slide that we had in the previous page, this one. In this slide, what we have, there is a table which is giving us the different values of n and c. And we've got to see the values, the computed values of n and c in the problem we are working is closer to which one of the values given in this table, and that one indicates the type of the tool material. Well, it's very obvious that if we take the values of this table or similar tables out, then the values of n, which is 0.137, and C141 is closer to say high-speed steels, and particularly the top row of the high-speed steels. So n of 0.137 is closer to the top row, and also C of 141 is closer to the top row. So the likely tool material is actually high-speed steel, which is used for cutting generally non-steel materials. It's closer to this one. Okay. So that's the solution to part B of the problem. And then let's move on to part C. In part C, we are asked to compute the tool life that corresponds to a cutting speed of 90. So cutting speed is now different. It is 90, and we are expected to compute the tool life on the basis of cutting speed of 90 meters per minute. What do? We make use of the equation up here again, the Taylor tool life equation. We make use of the equation. Now we have the values of n and c at hand. So if we substitute the value of v, we can compute the value of t, or the other way. If we substitute the value of t, we can compute the value of v, which corresponds to that given tool life. So by making use of the equation, substituting the value of v, which is equal to 90 meters per minute, and solving the equation for t, which is this one, then we substitute the values of c and n, and this results in a tool life of 26.6 minutes. So if we have the value of cutting speed, we can easily estimate the expected tool life for that given scenario. And in part D, compute the cutting speed that corresponds to a tool life of 10 minutes. Again, we make use of the same equation. Up here in this equation, if we know the value of, say, tool life, which is 10, we have the value of t, n, and c already computed. So the only remaining parameter to be computed is cutting speed. So we make use of the equation, substitute the values in it, and that gives us a cutting speed of 103 minutes. So on the basis of this given tool life, we can compute the value of cutting speeds. A cutting speed of 103 meters per minute gives us a tool life of 10 minutes. As you can see, cutting speed is significantly affecting the tool life. Just a small drop in cutting speed gives us a significant improvement in the tool life. So this is very useful in the actual work environments. If we have got limited, say, cutting tools available, we can estimate or compute the cutting speed, which makes it possible for us to proceed with the machining operation. Okay, is there any questions on this? No questions? So, making use of the Taylor's equation. Making use of the Taylor's equation makes it possible for us to estimate the tool life of the cutting tool, and when we are going to plan and estimate the tooling cost, this equation is very useful, giving us an estimation of the required number of cutting tools, and eventually we can estimate the cost of tooling for the given task. So this is very useful, and we are expected to know this very well when we are going to begin a production activity. Okay, moving on to the next problem then. Well, this problem is telling us that the outside diameter of a cylinder made of a titanium alloy is to be turned. So there is a cylindrical workpiece material. The material is titanium alloy, and we are going to perform a turning operation on the outside diameter. Starting diameter is given. The starting diameter is 400 mm, and the length is also given 1100 millimeters. So we've got the dimensions of the cylinder. Feed F is given 0.35. Depth of cut is also given 2.5 millimeters. The cut will be made on a cemented carbide cutting tool, whose Taylor tool life exponent is this much, and also C value is this much. So the values of the tool life equation are given. We know the value of N, we know the value of C, we know the dimensions of the workpiece material, feed and depth of cut are also given. Now, what do? Compute the cutting speed. Cutting speed, or V, is to be computed that will allow a tool life, or T, that is just equal, T is just equal to the cutting time of this workpiece. So we want to compute V, cutting speed, in a way that tool life of the cutting tool will be equal to cutting time of this workpiece, and cutting time, or TM. So we've got to compute cutting speed in a way that tool life is equal to machining time, TM. Machining time equation, we had that before in previous lectures. We had equations making it possible for us to compute the machining time of the cylindrical workpieces. And that is the one which I am taking it out from the previous lecture. This one is the equation making it possible for us to compute the machining time in straight turning operations. What do we have in this? Machining time TM. D is representing the diameter of the workpiece. L is its length. F, feet, and V, of course, is the cutting speed. Now, we are after computation of the cutting speed, so we don't have the value of V, but the values of all the other values in this equation are given, and also we do not know the value of TM. We do not know the value of TM. We do not know the value of V. All the other parameters are given in this problem. Okay, what do we do now? Let's take a look at the other equation, Taylor's tool life equation. The value of N is given, the value of C is given. V, which is the cutting speed, is of course what is to be computed, and the value of T is not given. So we do not know the value of T. We do not know the value of TM. But there is something which is mentioned in the statement of the problem. In the last sentence, it means that the cutting speed should be chosen in a way that it will allow tool life to be just equal to the cutting time. Just this bit of the statement of the problem. It's telling us that TM should be equal to T. So this is something that we can take advantage of this. So on the basis of what we have had so far, we know that TM is equal to T for this given problem. TM should be equal to T, and we do not know the value of either of these, and we've got to compute the V in a way that TM will be equal to T. What do we do? First, we write the equation for TM. We solve the equation for TM on the basis of the unknown value of V, which is this same equation. We substitute their values and we get this value. This is the value of TM, or machining time, on the basis of the unknown value of V, cutting speed. We do the same to the other equation. Substitute the values of N and C and compute T on the basis of the unknown parameter V. And this is what we get. We get the value of T, tool life, on the basis of V, which is yet unknown. Okay. On the other hand, we know that TM is equal to T. This is what was given in the statement of the problem. So we can equate these two equations with one another and compute the value of the only unknown parameter V. And that's what we do. If we consider TM to be equal to T, then we can equate the two equations that we have just developed, this one and that one. Now we end up in a single equation and only one unknown parameter, and that is the cutting speed. And then once we solve this problem, then we can compute the value of the unknown parameter, and that is cutting speed. A cutting speed of 226.6 meters per minute makes it possible for us to make use of a single cutting tool in order to cut the workpiece. Once the workpiece is machined, then the lifetime of the cutting tool is also reached, and we've got to replace it with another cutting tool if we want to cut another workpiece material. So all of the lifetime of the cutting tool is exhausted for machining of a single workpiece. Okay, is there any questions on this? Now, if we want to check the solution, what do? We want to see if what we have computed is correct. We can substitute the value of computed value of cutting speed in the above equations, in this one and also in that one. If the value of V is included in this and in that one, then it should result in the same value of T and Tm. Let's do it this way. Tm, if we substitute the value of, say, cutting speed in this equation, this is what we get. The Tm, or the cutting machining time, comes to 17.4 minutes. Now we substitute the value of V in the other equation we had just computed, and it gives us that same value for T, which is 17.4. So again, we have got the same value for Tm and T, and they should be equal according to what was given in the statement of the problem. So this is verifying that the computation is correct. Any questions? Well, let me ask you a question now. On the basis of what we had and what we learned in this problem, on the basis of what we have learned in this problem, what happens if we want to compute the cutting speed in a way that a cutting tool can be used for machining 2 workpieces instead of 1? In this problem, we made use of a single cutting tool in order to cut 1 workpiece, and then it is exhausted. We've got to replace it with another one. Now we want to compute the cutting speed in a way that it is possible to machine 2 workpieces with a single cutting tool. Then how does it change the solution of this problem? What has to change? Well, it changes this bit of the problem. This equation is only valid if tool life is equal to machine time of 1 workpiece. If we want to machine 2 workpieces with the same cutting tool, then tool life should be equal to 2 times of Tm, or 2 times of machine time. So this equation will change to 2 Tm is equal to T. If we want to compute n number of to machine n number of parts, if it is possible, sometimes it's possible, sometimes it's not. If we want to machine 10 workpieces or with making use of the same cutting tool, then 10 Tm will be equal to T. We've got to work out if it gives us a reasonable, say, cutting speed, then we will use it, because there is a range for the cutting speed. Within the acceptable range of cutting speed, we can utilize the cutting tool. But if it is giving us a cutting speed which is outside the acceptable range, then it is not acceptable. Okay, the comment from Michael, Tm could be different values. Yes, Tm could be different values, of course. If we change the cutting speed, Tm will change. If we take a look up here in this equation, well, as cutting speed is greater, then Tm will be smaller. As cutting speed is smaller, then Tm will increase. However, the value of V cutting speed is acceptable within a range. There is a minimum and maximum value for cutting speed if we take a look at the handbooks. So it is only acceptable as long as cutting speed is within the acceptable range and not outside the acceptable range. Okay, any more questions? Well, this is an important question and problem. We've got to make sure that we have a good understanding of this. And if there is a problem given to us for different number of parts, similar solution will be used. However, the equation that I have highlighted here, it will change slightly. Okay, moving on to the next problem. Well, problem 3, a turning operation is performed on a steel shaft with a diameter of 12.5 centimeter. And the length is also given to equal to 80 centimeter. A slot or keyway has been milled along its entire length. Well, we have got a workpiece material, rotational workpiece material, which has got a certain length, and there is a keyway or a slot which is machined all the way along the length. Okay. The turning operation reduces the shaft diameter. For each of the following tool materials, indicate indicate whether it is a reasonable candidate to use in the operation. Let's see what the choices are. A, plain carbon steel. Is this a suitable tool material to be used for cutting a steel shaft with a keyway on it all the way? Yes or no? What comes to your mind? Please say yes or no only. Plain carbon steel to be used as the tool material for cutting the steel workpiece with the keyway on it. Well, okay, Paul says no. And Michael, what do you say? Okay, no idea. Moving on. Okay, and then I will explain this later on. High-speed steel. Do you see this as a suitable choice? Okay, Michael said no as well. How about high-speed steel for this given material? The steel material is to be machined and there is a keyway on it all the way. Do you see high-speed steels as suitable materials for this? Yes or no? Okay, not sure. Moving on, cemented carbide, ceramic, and sintered polycrystalline diamond. Diamond is a brittle material. Ceramic is also a brittle tool material. Ceramics and diamonds are not suitable if there is an impact in the machining operation and if the cutting tool will be subjected to an impact. Is there an impact in this operation? Yes, there is. Okay, now let's take a look at the say one of the figures which I have included in the lecture materials. If we take a look at this slide which I have taken, a portion of the slide which I have taken out from the lecture materials, we can see that if there is an impact in the operation, and in this operation, because there is a slot which is machined all the along the lengths, it is subjecting the tip of the material or tip of the cutting tool to an impact. In every revolution, there is a small impact to the tip of the cutting tool. So it may result in fracturing the tip of the cutting tool. And because of this, we've got to choose a material, cutting tool material, which is resistant to impact. Now let's take a look at this graph here. As we can see, diamond, polycrystalline diamond, ceramics, and also coated up to coated carbides. Up to this point, these are the ones that have got a low resistance to impact. So for this given application, these ones are out because of low resistance to impact. And we are left with the rest. Within the rest, if we take a look at the cutting speed, we've got very low cutting speed for low carbon or plain carbon steel. So I will take this one out as well. What is left is just the remaining ones. We've got high-speed steels or HSS cutting tools, sintered cemented carbide, coated high-speed steel. This is not given in the statement of the problem, so this is already out. Coated carbides, this is not also given. So these two are out because these are not listed in the list of available tool materials. This is leaving us only with only two choices: high-speed steels and also sintered carbide ones. These are the ones that are giving us a reasonable cutting speed, which is not very low. At the same time, they have got high resistance to, say, impact. So these are the ones that are acceptable. So choices B and C are acceptable ones. So this is the solution. Only choices B and C are suitable for this material. If there is no keyway machined on it, then we can make use of all of the remaining ones, excluding the first one. However, because of the keyway, the last two are also excluded, leaving us only with choices B and C for this tool material. Okay. Is there any question on this? No questions. Okay, thank you. Moving on. Problem 4. In a milling operation with no coolant, a cutting speed of 150 meters per minute is used. The current cutting conditions, which is dry machining. Dry machining, as mentioned, as I explained in the lecture materials, lecture stuff, dry machining is now becoming a common machining process. There are issues with contamination of the coolant and its disposal, and because of this, many companies these days prefer to make use of the coolant, to make use of the dry machining, so that they do not face the problem of getting rid of contaminated coolant material. So it's very popular method these days. The current cutting condition, which is dry, yields a Taylor tool life equation. The value of N is this much and the value of C is this much. When dry machining is used, the values of N and C are as given in the statement of the problem. When coolant is used in the operation, then cutting speed can be increased by 20%. Well, we can increase cutting speed if coolant is used. Of course, it will help reduce the heat of the operation, so we can make use of a higher cutting speed. Still maintain the same tool life. So we make use of a higher cutting speed, but maintain the same tool life, which is T. Assuming N does not change with addition of the coolant, what is the new value of C? This is an interesting problem. So for dry machining, we are provided with the values of N and C. If we add coolant, we can increase cutting speed by 20%. The value of N doesn't change, and now we are in need of computing new value of C. And don't forget that we defined C as the cutting speed, giving us a lifetime of 1 minute. So when cutting speed increases by 20%, we are expecting that C will also increase by that much. This is what we had in the beginning of the tutorial session. Now we just make use of the equation for the Taylor, this one, and substitute the values as given. We substitute the values as given. It gives us a tool life of 45.7 minutes if we substitute the values of C, N, and the cutting speed of 150, which was given in the statement of the problem. So all the values are given. For the dry machining, we substitute all these values, and this is giving us a tool life of this much when dry machining is used. Now we add the coolant, and it was mentioned that as we add the coolant, we can increase cutting speed by 20%. Well, now this value of cutting speed, which was 150, will be increased by 20%, and this will increase to this much. Now the new cutting speed when coolant is used increases to 180 meters per minute from 150, which was used in the dry condition. Now we achieve the same tool life, so tool life also doesn't change. Now we are asked to compute the new value of C. What do? We solve the equation, Taylor's equation for C, as is presented here. We solve the equation of Taylor for C. Now we have the same value of tool life as it was computed. The new value of V, which is 180, and the value of N doesn't change. Substitute everything in it, which is giving you a different value of C, which is more than what it was. The value of C now increases to 468. And then if we take the difference, compute the difference of this new value of C and the one that was given before for dry machining, it gives us 20% of increase in the value of C. And this is what was expected, as C will increase by the same amount of, by the same value as V was increased. So V increases by 20%, C also increases by the same value of 20. And that is what is resulted from this problem, what is concluded from this problem. Okay, is there any questions on this? So one more time, keep in mind that C is the constant value, and it is interpreted as the cutting speed, giving us a lifetime of 1 minute. So in dry machining, V is something which is giving us a to life of 1 minute, and in say when we make use of the coolant, then the value of V will increase, and accordingly the value of C will also increase by the same value of 20%. Okay, there is one more problem here, which I am leaving it to you to be done at home. This is a student work, so read the statement of the problem. It gives you some different values of say feed and also depths of cut, different scenarios, and there is a problem which you've got to actually do the problem and make a graph on the basis of what is provided to you. So this is a student activity. I'm leaving it to you to be done at home. Okay, any questions? Okay, that's all for today. Thank you very much for your participation, and we will meet again next time.